So on the other hand, the other three state-of-the-art technique mentioned before completely fail to this memory rig error in the program snort. First, the boot fetches succeed in generating a patch itself, but it is unsafe patches, as this patch introduce user after free in this case. Likewise, leakfix and memfix also fail to fix this error in the program snort due to the limited fixing strategy and the scalability issues respectively. So from now on, let me explain how Sabre works using these toy code programs. And can you explain the error of these simple programs? Well, I will give you 15 seconds. Please find out why this program is buggy. I believe you have found this memory rig that the object allocated at line 1 is unreachable after line 7 when taking the first branches highlighted in yellow. We now know the cause of the error. So can you fix these errors? I will give another 20 seconds. Try to fix this bug by hand. For the hint, just inserting the free statement, the free P, is not the correct patches. It is more tricky patches. So please try to fix these bugs. Okay, now I will explain how to fix this error by using the Sabres. The Sabre first employs a static analysis to transform the program on the left into the object flow graph OFG, which is on the right. This OFG describes the life cycle of each object, such as O1 or O2. And a vertex of these OFGs represent a heap object at a certain program code line and a pass conditions. For example, this vertex highlighted in the green denotes the object O1 available at line 6 when the true branch condition, which is C, is taken during the program executions. Likewise, this another vertex represents the same object O1 at line 6 when the first branch condition, the negation of the C, is taken. And the edges represent the program control flow labeled with events such as free or use for the object. For example, these edges highlighted in the green indicates that this object O1 is freed when it flows to line 6 to line 7 under the condition, the true branch condition, which is C. And these edges with the label epsilon indicates no event occurs for the object O1 under the first branch conditions from the line 6 to 7. Okay, after constructing this object flow graph, Sabre tries to find the error path in these graphs. And when looking this sequence of the edges highlighted in red box, we can notice that it is on error path as this object O1 is allocated this object is allocated and used and is unreachable without being free, which is the memory rig errors. So after finding this error path, Saber tried to re-label the object flow graphs. So let's try to re-label the object flow graphs. For example, let's assume that we relabel the second edge of the, for example, the second edges of the, with epsilon as the edges with the free statement. But as you can see, this labeling is to introduce new errors, use after free. This object is allocated and freed and then used. So this is use after freeze. So how about, let's assume that we relabel the fourth edges with epsilon as the edges with the free statement, where it is a correct patches, as we know the object O1 is allocated and used and correctly freed and then unreachable. So this is the correct patches. So once the Saber found the correct relabelings, the next step is to convert the labeling into the patch at the source code levels. Saber can directly infer from the edges from that the patches should be inserted at the pre-statement between the line 6 and 7, where the pass condition is the negation of the C, which is the first branch conditions. So when you look at the source code, we can find this new patches code, which is when the first branch condition, which is the negation of the C, and we insert the pre-statement P. So in this way, Saber find the correct patches by using the constructing the object flow graphs. So the main issue of this technique is to construct the OFGs. However, constructing OFG for the real-world programs with hundreds of the thousands lines is very expensive. So to address these technical challenges, Saber used two heuristics for improving the scalability issues. The first heuristic is the program slicing heuristics, which is only leaves the program part relevant to a given program report. And the second heuristic is the path merging heuristic to selectively distinguish the promising paths. For example, we may have to separate the both sides of the branches B1 because the free statement is only feasible in the true branches. However, the distinguishing the branch B2 does not help at all, as all the edges consist of the epsilons, which is no event. So Saber merged these redundant paths into just one path. So based on these two heuristics, Saber was able to construct OFG for the real-world programs, thereby achieving the high repairability even for the large programs. And finally, let's see the effectiveness of the Sabers. Saber used the 10 open source C project for the evaluations, where the line of the code ranged from the 2000s to the 300,000s. And they compare to the repairability of the Saber with the one of the foot patch in terms of fixing the memory rig errors. And the static analyzer infer takes these 10 benchmark program as input and generate a total 162 error reports. And these error reports consist of 96 real errors and the 66 false alarms, which is not real bugs. So ideally, Sabre and the Footpad should not try to fix the errors for the false alarms because these are not real bugs. And as a result, Sabre was able to generate the patches for the 74% of the true alarms, where these are all the correct and safe patches, except for one bugs. And meanwhile, Footpatch was able to generate only the patches for 20% of the true alarms. And among them, the 5% of patches are unsafe patches, which is introducing new errors, and the 2% of patches are incorrect patches. More interestingly, Footpatch also generate the patches for the 14% of the false alarms, even though these are not reals. Also, these patches were unsafe, so introduced the new errors by the Footpatches. On the other hand, Sabre systematically reject any patches for all of the first alarms. Okay, let's summarize these lectures now. In this class, we continue to learn about the special purpose program repair techniques. In particular, we focused on introducing state-of-the-art techniques for fixing one of the prevalent errors in the open source project, which is memory errors. And we tried the 4 state-of-the-art techniques such as Footpatch, leakfix, and memfix, and Sabre from the 4 aspects, which are scalability and repairability and safety and correctness. And we learned about the core component of the Sabres. And the Sabre is the most balanced technique for fixing memory errors in the 4 aspects. Okay, this is the end of the lectures. Well, thank you for listening to my lectures, and goodbye, everyone.